All right, recording started. Sharing my screen. Okay, good evening. Today's topic, we will start a new section, which is transmission system overview and planning. Here, we will talk a little bit as an overview. So as we know, the electrical system, there is a production or generation, transmission, sub-transmission, and distribution. That's what we mentioned earlier. So the production can be from like the generation, the classical coal, the gas, combined cycle, all of them like those call it thermal, or they can be nuclear or renewable energy. Renewable energy can include photovoltaics, it can include wind and like hydropower, etc. There is also like water power, which is basically we call it like the ocean or the waves power. The other thing, there is the transmission. The transmission, as we mentioned, there is a high voltage in Jordan. There is 400 kilovolts, and there is, I would say, extra high voltage. I mean, let me separate it to different way. Like extra high voltage, like 400 kilovolts, and there is a high voltage like 132 kilovolts, 230 kilovolts, and also another example for extra high voltage like 500 kilovolts. And there is something we call it ultra high voltage, which is 1000 kilovolt, or sometimes they call it 1 megavolts. This is ultra high voltage. In Jordan, we have 400 kilovolt and 132 kilovolts, while the rest we don't have them. It used to be 230 in the past, but now it's no longer here. And 500 kilovolts, it's not in Jordan, but you can find it in different parts of the world. And the other thing, there is the sub-transmission. It can be as the 33 kilovolts, which is basically the medium voltage, or 11 kilovolts. Sometimes there's something like 66 kilovolts. This is very rare. Then the last thing, which is the distribution, which is 0.4 kilovolts, or in other words, this is line to line and line to neutral, which is 230 volts. That's in our system in Jordan. In other parts of the world, where is like, for example, like in the United States, they have the transformer 7.2 kilovolts that converted to be 205 or 120 volts if we are talking about line to neutral or line to line. So in the United States, the situation is different than what we are discussing here. Basically, just in summary, the distribution transformer for the for the United States, there is a single phase, 7.2 kilovolts as a single phase, or we can say 15 kilovolt as a three phase. But I'm talking about like single phase, 7.2 kilovolts. And there is a center tap transformer that you can take the here from here to here 120, from here to here 120, then the sum is 240 volts. That's the distribution transformer, again, like in the United States. But however, in Jordan and other parts of the world, we are using 230 volts. That's our system, and we are based on 50 hertz, while in the US, it used to be 60 hertz. Okay, so let's keep going. Here is.
Can I just ask a quick question before we continue?
Of course.
And why do we have like two systems, 60 hertz and 50 hertz? Like, why isn't it like worldwide, like everywhere, 60 hertz or either 50 hertz? Like, I know the American part of the world, they use 60.
Yep.
Or every country that had like American influence, like within the power grid, they have 60, such as KSA and Japan.
Right. Yeah, I like your question. Okay. So the thing here, let's think about the frequency definition. the frequency, when we say like it's 1 over the time or cycle per second. So when we say 50 hertz, this means 50 hertz, which means 50 cycles per second. Then 60 hertz, also 60 cycles per second. What does it mean, cycles per second? The overall waveform for the distribution voltage V of t equals square root of 2 for a single phase, 230 cosine 2 pi times f, which is 2 pi times 50 t. That's the V of t. Let me talk about phase A. That's in like Europe and Jordan. And in the United States, VA of t square root of 2, 120 cosine 2 pi times 60 t. So this is the frequency here, the frequency here. Okay, so what's the point of making the frequency 50 or 60? Or sometimes, in other words, why don't we make the frequency 100 hertz? Or how about if we make it 1000 hertz? Something like that. What's the point of making the frequency exactly 50 hertz or 60 hertz? So I think this is like the early invention of the electricity. As we know, DC was led by Edison, and AC was led by Nikola Tesla, who invented the AC and invented the DC. And as we know also, who invented the light bulb, which is the light bulb. I'm not sure the spelling of the bulb, pardon me, just like the lights. Who invented the light bulb, which is, I think the light bulb like this, Edison. So Edison invented the light bulb, even though he was in the DC, but he already invented the light bulb. Then the light bulb, when we say the frequency 50 hertz or 60 hertz, it is a cosine. So 50 cycle per second or 60 cycle per second, that's what does it mean. If we make the frequency 1 hertz, the light bulb will be on half second and off half second, which is something annoying. So there will be dimming on the lights. The light will start dimming, and that dimming is annoying. I mean, D-I-M-M-I, which will annoy us because you will see like fluctuating or like dimming when it is, if it is 1 hertz, which means 1 cycle per second, half second on, half second off. Or if we make it like, for example, 10 hertz, it will be changing the polarity every 0.1 second, which is kind of annoying. So therefore, they said, okay, let's make it higher. Then if we make it higher, it will be better for us. Then if we make it 50 cycles per second or 60 cycles per second, we will not notice the, the blinking, or which is called like the dimming, or so it will not be noticeable. Then therefore, let's make it high. So that's why we don't want to make it the first thing, like the first concern. That's why we don't want to make it very low value. How about making it very high value? Why don't we make it like 1 megahertz or 1000 hertz, something like that? The main reason is related to the speed of the generator. The synchronous generator speed from the electrical machine course, NS, equals 120F divided by the number of poles. So in order to generate power, the vast majority of the conventional generators are based on synchronous generator. So you will realize that the number of poles is constant. So the synchronous is related to the frequency. So assume we have 2 poles. Then, for example, NS will be 60 times F. So if we are using 50 hertz, then the speed will be 60 times 50. 6 times 5 will be 30, so it will be 3000 RPM. If the frequency is 50 hertz, then the frequency, 50 hertz, then the speed will be let me see, like 60, 50. Yep, I think 3,600 in the first one. Then the other one, 3,000 RPM. So we will realize that 3,000 RPM is very large value. So how about if we make the frequency 600 hertz? This yields to be 30,000 RPM, which is something, I mean, the generator can be very big, like um, the conventional generator can be bigger than the classroom. So if you increase the speed, the faster generator, which will make the higher rotational losses, it will start vibrating. There will be a lot of rotational losses, and it will impact the mechanical structure of it. So therefore, our target is to reduce the speed of the synchronous generator as much as possible. So there should be a trade-off: increase the frequency to remove the blinking of the light bulb, or, and the other thing, decrease the frequency to remove the impact of the rotational losses and the vibration of the generators. So in order to make it a trade-off, they said, okay, let's make the 50 hertz, and let's make, I mean, United States, they did the 60 hertz, the researchers there, while the researchers in the Europe, they did 50 hertz. Everybody did it in their own. What's the benefits? I would say like 60 hertz, you will see like more rotational losses, while 50 hertz, less rotational losses. But regarding to the efficiency, they realized that the 60 hertz more efficient than the 50 hertz. Then we said that, okay, there are different, I mean, aspects. Which one is better, 50 hertz or 60 hertz? I cannot judge. I mean, both of them, they have pros and cons. Like some of them, they have better efficiency. The other one can be lower rotational speed, lower rotational losses, which is, I would say, like better for the mechanical structure of the generators. That's, I mean, an aspect. The other thing also, which is the 120 volts or 230 volts. Which one is better? Um, I would say like there is nothing, I mean, we cannot also judge which one is better, but 120 volts, I would say, is safer in terms of the, if there is some fire, because 120 volts lower than 230, which is make it safer. But the problem associated with 120 volts, some applicants are not sufficient to be working on 120 volts. Therefore, you will see in these countries, like for example, like in the United States, you will see a dual voltage. You will see some plugs that are working with 120 volts. Some other plugs are working with 240 volts. I think it's also in Saudi Arabia as well, like in some other parts of the world, they have 120 and 240. So sometimes, I mean, the drawback of that, like maybe you will miss a plug. You will connect the power for 120 volt device to 240, which will make it burned out. The other thing, again, 120 is safer, but sometimes it's not sufficient to supply some large power elements like the air condition units or water heater. It can absorb a lot of power, which make 120 volts insufficient. Therefore, the central air condition in the United States homes is connected to 240 volts. The air, I would say, like the water heater, it's also connected to 240 volts. The air, what's called the air dryer, it's connected to 240 volts. However, the rest of the home is connected to 120, like the lights, the sockets, the outlets, the kitchen applicants, all of them are connected to 120 volts. Again, like which one is better? I don't know, but I mean, everyone has its pros and cons, and we need to make sure that we are familiar with each one. The other thing, in Japan, Eastern and Western, each one has its own system. So 50 hertz and 60 hertz. Why there's a difference? The main reason is in Japan, when they started connecting the electricity, Eastern Japan, they just did it. I mean, Eastern and Western, they were disconnected. So they started on 50 hertz, and basically the Western, they started on 60 hertz. Then they started in their own. and they didn't, I mean, plan for the future, or they didn't thought that they will be connected sometime or at one day. So they started as a different grid. They started a different grid, like the grid of the West and the grid of the East. Then later, after they expanded, they forced to be connected. Now another question, which is Eastern Japan and Western Japan are connected, right? But how are they are connected? They are different frequency, different voltage. How can they be connected? So here is the 60 hertz and here is the 50 hertz. How there's a great connection between Eastern and Western? The thing is, basically, we can use power electronics by converting AC to DC. And here, the same thing, converting AC to DC. Then they are linked here together. So using power electronics. So this is AC to DC, allows a bidirectional power flow. So it's working on both inverter and rectifier, and the same thing here. Then we can do a power exchange as needed, as much as needed, by using power electronics. Again, AC to DC, DC to AC. So they will do the job, and it is bidirectional. So it allows the power to go from one way to the other way, and the vice versa. That's how they are connected, like Eastern and Western Japan, because they have different frequencies. So in summary, like to answer your question, which one is better? We don't know. I mean, I don't know. I cannot judge. But why there is a 50 hertz and why there is a 60 hertz? United States, they started as 60 hertz, just how they established it. And then Europe, they started as 50 hertz, the startup of the electricity. They just decide, let's use 50 hertz, and the other one, let's use 60 hertz. Then they became a standard. While why we used 50 and 60, why we didn't use low value? Because again, because the light bulb, we don't want to see the blinking of the light bulb. And why we didn't make it too large value like 1000 hertz, or because we don't want to make the very high speed of the generator. Okay? So, I mean, it's a small question, but it is deep in concept. So I like your question. Thank you.
Yeah, thank you so much.
You're welcome. Now, let's keep going here. Here is the the plan. How is the power? You see like the towers. These towers are the high voltage and extra high voltage, which is associated with the transmission. Then there's a distribution here. This is, I mean, there's a substation here. This substation, I mean, it's called distribution substation, but I disagree with this definition. It's not distribution. It is a substation. Distribution substation associated with the low voltage. So this substation, basically, let's assume this is 132 kilovolts. It will convert it to be 33 kilovolts. So you can look at it. It was towers. These big towers are high voltage associated with the transmission. Now, these poles are medium voltage poles and associated with the sub-transmission. Okay? So I think I think you have seen this before. So you have seen the towers, you have seen these poles. There are many misconceptions. People say high voltage poles. They are not high voltage poles. They are medium voltage poles. Or many people say like عمدان الضغط العالي, or so they are not الضغط العالي, they are الضغط المتوسط, عمدان الضغط المتوسط. So those are within the sub-transmission scenario. Then after that, the sub-transmission will connect power to the customers. But in order to connect the power to the customers, you will see here in the pole something is called the distribution transformer, which is DT. We mentioned this before in previous lectures. So that distribution transformer converting 33 kilovolts to 0.4 kilovolts, which is the voltage that goes to your home. Okay, so there should be a distribution transformer on each neighborhood. Here's a distribution transformer. This is an industrial area, so there is a distribution transformer there. Then there is also another power line that goes to the customers, other customers, but this one, it goes as again another 33 kilovolts. Then from here 33 kilovolts, it goes as a main feeders here to the home. Then there's 33 kilovolts to 0.4 kilovolts. Here it goes to the industrial areas as well, and so on. That's how it goes to the homes. So this is the overall map. Then you can just like have a clue about the transmission and distribution as we see here. And you can imagine that's the poles. Uh, they are medium voltage poles. They can be either 33 or 11 kilovolts. Most likely inside the downtowns or inside the cities, there will be 11 kilovolt and most likely underground cables. But outside of the cities, you will see maybe 33, very few 66. I mean, it's very few. It's no longer in service. I think no longer in production. But you will see the vast majority are 33 kilovolts and very rare 11 kilovolts. But you can see. Now, the other thing about the power system. The current power system is based on a unidirection power. What does unidirection mean? The power goes from the substation toward the customer. Substation toward the customer, generation toward the customer, which goes only one way from the utility to the customer. But this is not the future. The future, as we know, there's a renewable energy. So the customers start producing power. So you as a customer, you are starts generating electricity by using photovoltaics panel, or like there's a lot of photovoltaics for solar farms, wind farms, which makes the power to be bi-direction, which means you as a customer sometimes can supply power, sometimes you can absorb power. So which is allow a bi-direction. The other thing, electric vehicles technology. So your EV starts charging electricity, and sometimes in the future, the power company can have the option to make discharge or to sell power to the grid, sell power from your EV battery to the grid. Why we are doing this? Because sometimes there will be in the future, as I mentioned in the last lecture, there will be um, a smart tariff or tariff based on peak off peak or evening period, morning period, and nights period. So each period has its own tariff. So I would say during the peak, which is during the evening, the energy prices are very high. So maybe as a customer, you can sell power from your EV to the grid because the energy prices are very high. Then you can earn some money. And during the nights, the energy prices goes down. So, for example, during the evening, the energy prices can be, as an example, 20. Um, I would say like 20 or 200 fills per kilowatt hour, while during the night it is 50 fills per kilowatt hour. So why don't you take the advantage and discharge your vehicle, sell power when it is during the evening period, and during the night you can buy power, charge your EV by 50 fills per kilowatt hour. So the difference is 150 fills. Then you can gain some money, right? Yes, right. But there's a drawback. What's the drawback? The lifetime of the battery, because there is a limited number of charging and recharging cycles. So this will impact the lifetime of your battery. So it's a trade-off. Just that you need to keep in mind. Then I would say again, the modern power system, it is, or the future power system as well, allow a bi-directional power flow, which is something very challenging because all of the transformers, distribution transformers, are based on our unidirection power flow. All of the protection associated with the power system are based on a unidirection. All of the our studies based on unidirection. Now, how about if we have more generation than the load? Where are we going with the extra generation? Where are we gonna supply to the grid? Okay, so what's happening next? Where should we store that power? So this is something that's really annoying the electricity right now. And this is something like there is, I mean, a disadvantage of the renewable energy because we have this sometimes a bidirectional power and we don't know where to handle it. So for example, if you need to connect renewable energy to the grid, you need to get an approval from from power company. Then to get the approval, they will make several studies and they will say, look at the distribution transformer and look the customers, all of the customers who are connected with this distribution transformer, they need to make sure the number of renewable energy will not exceed 30% of transformer capacity. Transformer capacity will not reach more than 30%. Why it will not reach more than 30%? Because we don't want the power to go back from the distribution transformer to the grid. So we want this distribution transformer to be only working as a unidirection. Even though there is renewable energy, so if we maintain the 30%, then your home have a photovoltaics, your neighbor don't have photovoltaics. So basically, you are selling power to the grid, but you are really actually feeding your neighbor. You are not selling this through the transformer. I mean, if your home is connected to the photovoltaics panel, your home is not supplying power to the medium voltage. No, this is not. So what's happening? You will supply the other customers. That's what's happening in real life. So the renewable energy sources connected in low voltage, they will be only within the low voltage range. They will not go to the medium voltage. So you will not see any medium voltage go to or you will not see the distribution transformer start to be as step up transformer, which is converting low to medium. No, no way. All of the distribution transformers that we have here are just step down, which is basically a unidirection. That's a challenge. That's why right now the current protocols, they say it will not exceed the 30%. If you need to exceed more than 30%, or if it succeed, or if you need to install renewable energy, maybe the power company will replace the transformer by a bigger size transformer, or they will tell you, okay, we will make a new transformer for you so you can connect photovoltaics to your home, or they will basically say, no, you cannot connect because it's already reached the capacity. So again, the thing about it, because it's only based on a unidirection, and that's what we have. The bidirection, we are not ready for it yet. Okay, how about the distribution farms? How about, I mean, photovoltaics farms or the wind farms? The photovoltaics and wind farms, they are based on a generation, not based on supply, not a bidirectional. What I mean, and when there is a wind farm, the power goes out. It will not go in. So again, it is what? It is a bidirection, unidirection, not bidirection. It's based on a unidirection. So in photovoltaics farm here and wind, I mean photovoltaics and wind farms, all of them are based on a unidirection, just one direction. While at home, it's the only way that we have bidirection at home. And at home, they are making it in a way it will not do a bidirection on the distribution transformer. So a bidirectional power is a challenge, and we are doing a lot of research about it. And actually, there is one research that I'm currently working on in replacing the distribution transformer, replace distribution transformer by something called solid state transformer, because distribution transformer is only unidirection, while the solid state transformer is a bidirection. Then if we can do that, the problem of 30% will no longer exist, while here the 30% still exists. Then we can solve this issue. I'm working on that actually. So I'm doing some research. Not only me, many researchers are doing that research by replacing distribution transformer by solid state transformer. And also the good thing about it, I mean, it is less losses. And the other thing can solve power quality issues. So there will be several advantages about it. And the thing about it, I mean, how I'm imagining like the future, we will see that distribution transformer, we will start no longer using it. We'll start in the future projects to use SST, but it's not mature yet. Not now, not after 10 years, maybe after 20 years, I'm not sure. It depends on how's the technology. Who knows? Maybe after 10 years, if it's mature enough, it will be fine. But I doubt about it. So I believe maybe the next 20 years, they will start to see this technology applicable. Anyway, so the thing about it, let's, I mean, recall the computers, the computer hard drive.
Can I ask a quick question?
Sure.
Yeah, do you think if we like reach a point in the future where like batteries are very efficient and they're very cheap, would you think that we'd entirely get rid of the electrical grid and like every home would have their own PV system or wind farm connected to a battery? Like rather than have a big grid connecting the entire country, you'd have like localized grids, like in a neighborhood,
Yeah,
supplied by PV power and like batteries, and that's it.
yeah. Um, the thing about the batteries, which is the life cycle and the lifetime, and the other thing, which is when like the battery can survive 5 years, 10 years after that, how can we recycle it? Which is will be harmful for the environment. So the thing about the battery as ion lithium, um, there is, I mean, a lot of research to try to like improve it, improve the life cycle, improve the capacity, but it still has a limitation. So I do think, I mean, the battery will, I mean, ion lithium battery will be mature sufficient in the future to solve issues. I mean, we can expand the life cycle, expand the lifetime, but the thing, it's still like limitation on the lifetime. So the thing, the answer about it, try to find different sort of batteries, not ion lithium. So, for example,
Solid state
that's
batteries.
there is we call it fuel cell, or I would say like hydrogen fuel cell battery or hydrogen battery. There is a nuclear battery as well. Not sure about the spelling of the nuclear, but you get it. Nuclear battery. So I would say nuclear battery is very harmful. I mean, I would say it's very dangerous. The fuel cell hydrogen battery or the fuel cell battery, this is, I mean, under research and developments, R&D. There are very few commercialized, but they are not commercialized yet. But they, I believe, in the future, they will replace the batteries by fuel cell batteries, which is hydrogen. You have the water H2O, so you have H2 or H store the hydrogen, and the how it can you just separate it, and the output of it O, which is oxygen. That's will not be harmful for the environment. So just H2O, O oxygen, and H2 go for hydrogen tank, and that's it. That's, I mean, the simple about it, which is um, environment, environmentally friendly or friendly for the environment. But the thing about it, hydrogen is dangerous, which is explosive. So there were, I mean, a lot of research about making hydrogen fuel cell as the as a battery instead of the regular battery or lithium or whatever battery that we have. Um, it's applicable. We can do it. But how about if there's a car accident? Then there will be explosion because of it. So it will be very dangerous. Then they're trying to figure out about the safety. That's the challenge, which is safety. How can we do that in safety? So the safety, in order to make it safer, one of the option, like airbag. So if there is an accident, there will be an airbag for the like the car. Then why did we do something similar to airbag? If there is something wrong happening, then there will be something release the gas or release the hydrogen. If there's an accident, it will release the hydrogen in the air before an explosion happening. And this can be a good solution. But we still like they're still observing this. Right now, um, they are doing it in the e-boats, electric boats. They are putting hydrogen in e-boats, electric ship and electric boats using hydrogen. This is applicable, and I think many research are doing it. One of the universities, University of New Orleans, UNO, they are doing a research with the power there, which is called Entergy. There's a company called Entergy. They are doing a research about it. This in the United States, in New Orleans, in Louisiana states. Um, they are doing a lot of research about electric ship and electric boats. In the Gulf here, in the Gulf there's a Gulf of Mexico. In the Gulf of Mexico, they are trying to make electric ship. And why don't we use the hydrogen there? And as we know, or actually the accidents on the electric ship is not as frequent as in the cars. So it will be, I mean, the safety protocols will be less compared to the cars, the regular cars. But it's, I mean, there are research going on in doing this in e-boats and also in doing it in electric plane, e-plane, airplane, electric airplane. So in electric airplane also, the hydrogen is the energy density is very high and very low in weight. So this is a perfect application about it. So no longer to use ion lithium battery. And there is another also, by the way, there is different parts, not only ion lithium, there is cadmium batteries and there's some other parts. But anyway, those part our target is to not use these batteries. So there is also, as I said, like in the airplane, there is we can use the hydrogen battery, but the drawback of the airplane is the during the landing and takeoff. I would say like during the takeoff more than the landing, because during the takeoff, the airplane is consuming too much. Too much fuel, which battery sufficient to do that. So that's why there's a concept. I mean, it's a very wide topic. There is concepts called hybrid airplane. Same thing to hybrid vehicles. There is a hybrid airplane, so that it can work during the takeoff with fuel, and when it is reaching a certain elevation, it will start to work on electricity or electrical airplane. I mean, again, there are a lot of research about it, but they are not commercialized yet. The only thing commercialized is the ion lithium batteries, but you will see in the future the fuel cell will replace the ion lithium battery. Okay? So the answer to your question, which is, can we replace, or we will see like rely 100% on the batteries? Right now, no. In the future, if they find the solution for the fuel cell, there might be a possibility, but still there are a lot of issues about it. Why there might be, why it's not 100%? I mean, it's very long topic, but I would say there is something we call inertia. The inertia is needed for the power system. So if your system based on the batteries and renewable energy without the traditional generator, there will be zero inertia. What does zero inertia mean? It means there will be a load fluctuation, or if there is a high power consumption, it will be energy drop significantly or energy raise up significantly. For example, try to consume too much fuel in once or in power, you will see the battery starts off the battery voltage drop, a significant drop in the voltage of the battery. then after that it will start recover smoothly. However, if there is an inertia, it will prevent this from happening. And that inertia happening because of the uh, generators. I mean, talking about the inertia, it will take a couple of lectures. If it will take a long time. But I would say just the drawback of, even though if we can solve the issue of the batteries, if we can solve the issue of renewable energy, there's still a big challenge about it related to the power system stability, which is related to the inertia. If there is no inertia, um, there will be a big problem. So the inertia is needed, is required. That's why some research are going on, is try to make something, we call it virtual inertia. I think virtual inertia. So many research are trying to solve this issue. So the thing again about the renewable energy, whenever try to find a solution, we will get to another problem. Then find the solution, get to another problem. The first solution or the first problem, no energy storage. Then okay, let's use hydrogen. Okay, using hydrogen, no inertia. Use virtual inertia, we will see a stability problem, and so on. And unless I think we might find a solution in the future, yes, we can find it. But it requires, more research. And we need, a clever guys like you, so we can think about these possibilities, this solution. There's something also I would like to mention for you about the challenge, renewable energy challenges in Jordan. Let me share this picture for you. This picture from Energy and Mineral Resources Commission, EMRC. We already talked about it last lecture. And we see like this comes from a recommendation from NIPCO. NIPCO make a recommendation to EMRC, and EMRC, they made it to GIPCO, ITCO, and ITCO. So we can realize that they mentioned it during Ramadan, there will be a light loads, and dry light loads, they need to disconnect the renewable energy. Oh, we need to disconnect the renewable energy resources. And they're asking the distribution companies to disconnect the power from Fridays and Saturdays every week, and during also the Eid, during the holidays, during the holidays, no matter if they are Eid and the other thing, holidays, and during Jum'ah, Sabbath, which is Friday and Saturday, uh, and even sometimes during the normal days, if they were asked by NIPCO, starting from Ramadan until the end of Nisan or end of April. What's the point of that? Why they ask us to do that? Any clues? What do you think? Why? Any clues? Do you think? Do you have any thoughts?
Our consumption would be too low, so they don't want excess energy overflowing.
Okay, that's okay. Yeah, our energy is, consumption is too low. But even though if it's too low, the amount of renewable energy supplied will be sufficient to give us electricity. Will be sufficient. Will be more than enough. Not, I would say, take all of the renewable energy, but you still need more energy. You need to connect the. I would say, let me give you an example. Assume we have renewable energy 1 gigawatts. Our minimum load is 1.5 gigawatts. So the renewable energy, even though all of the capacity is still below than the capacity or below than the minimum load. Um, One of the things about it, which is if we use all of the renewable energy, then we will reduce the usage of fossil fuel, reduce the usage of inertia, then we will be less inertia, which will make the power system unstable. So that's one of the things related to the inertia. The other thing related to the load curve. What do I mean by load curve? Let me draw something here for you. Here is the load curve, regular load curve. Okay. So the load curve here is like from 12 a.m. until 12 a.m. So here the load is very low, then start going up because people working up and going to work. Here is like 6 a.m. Then in manufacturers are working, industrial loads are working, like there is a motors, industrial cities are start working. So here is, for example, at 12 p.m. Um, I would say yes, starts. Then people start leaving their work, going back home. Then during they're going back home, the load will be low. Then when they reach home, the load will be high. Then after, um, I would say like 7 p.m. at sunsets, it will reach the peak. Then people start sleeping, then it will be low. That's the curve of the load. However, let's draw the curve of the renewable energy. It will start the renewable energy when between sunrise to sunset. So this is the duration. Then it will start then going back, going up. So look at the peak. The peak of the renewable energy different than the peak of the load. So different peak between renewable energy and load. That's impact a lot. So look at the minimum load here. If the photovoltaics can cover it, the remaining power will be supplied by fossil fuel or thermal stations. However, look at off-peak here, the amount of power that will be consumed here will be supplied here by thermal station. So in the thermal station, you will see the gap is very big. So assume here, for example, it will work as 0.5 gigawatts, and here it will work as 4 gigawatts. You see the gap? Very big gap for the thermal substation. So why? Okay, there's 0.5, then there's 4 gigawatts. Can we do it? Can we supply 4 gigawatts? Yes. Can we supply 0.5 gigawatts? Yes. So what's the problem? The problem is increasing the generation from 0.5 gigawatts to 4 gigawatts in few hours. And decreasing 4 gigawatts to 0.5 gigawatts in few hours. This is almost impossible. Or we can do it, you can do the increase instantaneous by doing which is turn off thermal units. You can turn off the thermal units. But if you turn it off, you cannot turn it on back easy. You need to wait maybe one day. Sometimes you need to wait 12 hours to be cooling down. Then after that, turn them back on. So the thing about the thermal, you cannot turn it off and turn it on immediately. If you turn it off, it will take maybe again 24 hours, some of them 48 hours, some of them 12 hours to be turned on back, to be back on service. That's also a challenge. Then there is a big gap between the thermal substation generation, between the peak of the renewable energy and between there is no renewable energy at all. That's the problem. That's things that cause the problem. That's why they said we don't want this, because during weekends the loads will be very light here during weekends. During weekdays they are not doing it because the gap is very big. The gap is 1 giga, not maybe 0.5 giga, something like that, or 1.5 giga. So I would say during weekends, the gap will be very low, or I would say the consumption will be very low. So this is also related to the customer behavior and related to the renewable energy. The customer behavior, we don't have access to the customer behavior. We cannot change the working hours. We can advise the people please don't charge your EV at evening. Please charge it at night or after 11 p.m. We can recommend this, but we cannot force. In the future, I expect to see this in the near future, to see like tariffs based on the time. We already have it on the commercial areas, but we don't have it in residential, but we can have it in residential. So you will see like there is a peak tariff or evening tariff, night tariff, and day tariff. So we will say that evening tariff is more expensive. So we will say, okay, so this will force the customer not to use or not to charge your EV, or not to use your air dryer, or not to use your washer during the peak time. So if we are doing this, this will reduce the amount of consumption, or will reduce the peak load on that. Okay. So again, here I hope this answered your question, which is basically there's a problem. Now here is the goal. Here is the thing about you. Now, since we are researchers or you are an engineer, we are problem solvers. Can we solve this issue? Can we avoid this thing? Because when they are turning off the renewable energy, it means we are not using a free energy, right? The renewable are just free, just come from the sun or come from the wind. Then during this time, this means like we are turning off the power, not using the renewable energy power 6 hours or maybe sometimes 8 hours. This makes it unfortunate. We are losing around 1 gigawatts or 2 gigawatts. If you make it like gigawatt hour, maybe can buy 1 gigawatt hour or 2 gigawatt hours per day. This is, a huge amount of power. What are we gonna do with this? Is there a way? Yes.
Like we can store them in other ways, like rather than batteries. Like for example, if you can use motors to pump water from under a dam over the dam, like pump it up, so like basically get stored as potential energy.
Yeah, we have hydropower in Jordan, and we have also energy storage systems that's the capacity about 1 megawatts. We already have it also, like we call it a distribution system, energy storage system substation. We have it, and we have a hydropower as well. Yes, we can do that, but do we have enough resources to do that? Do we have enough dams to do that, or do we need to build a new dams or build not dams, build like in the mountains, go to mountain areas and make a reserve of water and down the hill and up the hill? Okay, we can. This can be an answer, yes, but how much does it cost? Do we have enough funds for that? It's brainstorming about it. So I'm letting the answer open because they still couldn't find a real solution for that. The main reason is, yes, we have a good ideas, but it's not economically, we cannot handle it, or we don't have enough money for that. So I'll let this for you. Just think about it. Then maybe in your graduation project, you can work on it. Or if you are curious about it, you can just contact or I will be very happy for you if you I can maybe I can be the bridge between you and NIPCO. We can contact them, and if you need to do some research, doing a student research paper, you can do it on that. Okay, let's keep going.
Well, here's a wild idea, if I may
Yeah.
say. Isn't there like different بيسموها ساعات كهرباء for houses and for electric cars?
So different work. Do you mean
We have different ساعات
meters?
كهرباء. Yeah, meters for houses and for electric cars.
But the problem is not only the EVs. Are
No,
you talking about which problem? Are you talking about the problem here, this one?
yeah, that problem. Like
Yeah.
we could, rather than disconnect it entirely, we could just store them in EVs.
Okay, that's good.
Since we have a lot of EVs in Jordan, I think we're the second per capita after Norway.
Yes, but do we have enough EVs connected directly to the grid? That's something that we need to make sure they are plugged into the grid. Then you need to pay money to establish like EV charging stations in everywhere. And also maybe you need to pay also some money for the universities or the governments, so they can put it in their parking lots. So when they are at their work at 12 p.m., they are already in their work, then they can store the electricity stored from the, for example, like the renewables, etc., whatever you have. Yes, we can do that. This is a good, I mean, this is a great thing, but can we make it in terms of gigawatts? That's also something, I mean, maybe we can. This requires an economically study to check out about the feasibility. So yeah, I think this, I mean, a good thing, a good approach, but we need to think deeply about it, about how feasible it is. Thank you. Okay, let's look at it. So here, just like quick recall about the concept of reactive power, real power, and active power. The reactive power, which is basically look at the real power, the chips, apparent power, the whole bag of the chips. The whole bag of the chips, which is S, apparent power, and the assume you are purchase these chips and open it, leave it for a couple of days and go back to start eating it. It will be no longer fresh, right? Why? Because it will be there was a material inside the chips like filled with nitrogen and filled with gas that keep it fresh. Once you open the chips, the bag of the chips, that's gas that keep it fresh will disappear in the atmosphere. So the thing here, this is the reactive power. This is the nitrogen that keep the chips fresh. If it is once you open the bag, it will disappear. While what you are actually eating, not that nitrogen, you are eating the chips. This is the real power. But what you are paying for, I mean, what you are purchasing the whole bag, which is real and reactive power. That's happening for the industrial customers, which is we are worrying about reactive real and reactive power, and they are looking at the apparent power. However, what we are paying on residential, we are only paying the real power. But overall, as I said, like we need to understand the difference between reactive power and real power. Real power, that's what we're really consuming. Reactive power is essential, but at the same time, we don't want to make it too much. Okay, I believe let's stop here because we don't have enough time and the time is over. Okay, so I'm gonna stop here. Any question? Recording.